Hello learners, you must have played carom board, right? Isn't it fun for all of us? But have you ever wondered what is that powder we use to reduce the friction in that carom board? You also must have seen that coal is used in villages to cook food. Diamonds are used for making beautiful ornaments. Aluminium foil is also our day-to-day companion in tiffin box. What are these things made up of? Well, diamond and coal is nothing but carbon. The foil is made up of aluminium and the powder is boric acid, which is made up of boron. These elements, carbon, aluminium, boron, etc. belong to the p block. So, let us understand the various prospects of p block elements. After today's discussion, you will be able to locate the p block elements in the modern periodic table, write the electronic configuration of p block elements, describe the trends in atomic radii, ionization enthalpy and electronegativity of especially group 13 elements, explain the physical properties of group 13 elements, and appreciate the stability of lower oxidation state due to the inert pair effect. Understand the reactivity of group 13 elements towards air, acids, alkalis and also halogens. Appreciate the anomalous behavior of boron. So, the first question that arises is, what are p block elements? P block elements are those elements in which the last electron enters in any of the 3 p orbitals of their respective shells, and since a p subshell has 3 degenerate p orbitals, each of which can accommodate 2 electrons, therefore there are 6 groups of p block elements. The 6 groups of p block elements are numbered from 13 to 18. The characteristics of p block elements includes the general electronic configuration, which is Ns2Np6 except for the helium, whereas the inner core electronic configuration may differ. Just because of this difference in the inner core, there are changes in both physical and chemical properties of the elements. The oxidation state of elements in p block is maximum when it is equal to a total number of valence electrons, that is, the sum of s and p electrons both. One of the most interesting facts about the p block elements is that it contains both nonmetals and metalloids. P block elements show oxidation states other than group oxidation state, which may differ from the total number of valence electrons by a unit of 2. The oxidation state 2 unit less than the group oxidation state becomes progressively stable for the heavier elements in each group, and this fact is sometimes attributed to the inert pair effect. Now, the question is, what is inert pair effect and what is its consequence? Inert pair effect is the tendency of 2 electrons in the outermost atomic s orbitals to remain unshared. The term inert pair effect is often used in relation to the increasing stability of oxidation state that are 2 less than the group valency for the heavier elements of the p block elements, and its consequence is that it increases the stability of lower oxidation state as we move down the group. The first member of p block differs from the remaining members of their corresponding group in 2 major respects. First is the size and all other properties which depend on size. The second important difference, which applies only to the p block elements, arises from the effect of d orbitals in the valence shell of heavier elements, which start from the 3rd period onwards and their lack in 2nd period elements. For example, while boron forms only tetrafluoroborate, but aluminium gives hexafluoroaluminate ion. The first member of the group differs from the heavier member in its ability to form p-pi multiple bonds to itself and to other row elements. The heavier elements do not form pi bonds, but this involves d orbitals, that is d pi p pi or d pi d pi. Here we will study the chemistry of p block containing groups, namely group 13 and group 14. Now, let us start our study with group 13 elements, also known as the boron family. Boron is a typical non-metal. Aluminium is a metal but shows many chemical similarities to boron, and gallium, indium, thallium and nihonium are almost exclusively metallic in character. The abundance of boron in Earth's crust is less than 0.0001% by mass. Aluminium is the third most abundant element in the Earth's crust, that is 8.3% by mass. Gallium, indium and thallium are less abundant elements in nature. Nihonium is a synthetically prepared radioactive element and the half-life of its most stable isotope is 20 seconds. Moving to the electronic configuration. The outer electronic configuration of these elements is Ns2Np1, as the element boron and aluminium have noble gas core, while elements gallium and indium contain d electrons, with element thallium containing d as well as f electrons. The electronic structure for the first two elements is much less complex than the other elements of the group. Trend of atomic radii in the group. On moving down the group, for each successive member, one extra shell of electrons is added and therefore atomic radius is expected to increase. However, there is a deviation observed as atomic radius of gallium is less than that of aluminium. The presence of additional 10 d electrons offer poor screening effect for the outer electrons from the increased nuclear charge in gallium. Trend of ionization enthalpy. The ionization enthalpy values do not smoothly decrease down the group. The decrease from boron to aluminium is associated with increase in size. The observed discontinuity in the ionization enthalpy values between aluminium and gallium and between indium and thallium are due to the inability of d and f electrons to compensate the increase in nuclear charge due to their low screening effect. The electronegativity down the group is observed to be first decreasing from boron to aluminium and then increases marginally because of the discrepancies in atomic size of the elements. Boron is a non-metallic in nature, being hard and black colored solid existing in many allotropic forms. Boron has unusually high melting point due to its very strong crystalline lattice. All of the members are soft metals with low melting point and high electrical conductivity. Density of the elements increases down the group from boron to thallium. Moving on to the chemical properties of group 13. Let us study about the oxidation state and trends in chemical reactivity. As the first three ionization enthalpies of boron is very high due to its very small size, it doesn't form +3 ions and forces it to form only covalent compounds. But aluminium is a highly electropositive element and forms +3 ions very easily. However, when we move down the group, poor shielding effect of intervening d and f orbitals increases the effective nuclear charge, which holds ns electrons more tightly, thereby restricts their participation in bonding. As a result of this, only p orbital electron may be involved in bonding. Gallium, indium and thallium observe both +1 and +3 oxidation states. The relative stability of +1 oxidation state progressively increases. In thallium, +1 state is predominant and +3 is highly oxidizing in character. The compounds of group 13 elements behave as Lewis acids in their trivalent state. In trivalent state, number of electrons around the central atom remain only 6. Such electron deficient molecules have the tendency to accept a pair of electrons to stabilize, hence behaving as Lewis acids. However, The tendency to behave as Lewis acids decreases with the increase in the size down the group. Boron chloride easily accepts a lone pair of electrons from ammonia to form BCl3.NH3. The shape of BCl3 changes from planar sp2 to tetrahedral sp3 as shown on the screen. In trivalent state, most of the compounds being covalent are hydrolyzed in water. For example, the trichlorides on hydrolysis in water form tetrahedral species in which the hybridization state of element is sp3. On the other hand, aluminium chloride in acidified aqueous solution forms octahedral ion. In this complex ion, the 3d orbitals of aluminium are involved and the hybridization state of aluminium is sp3d2. Now, let us solve a problem together. The problem is that the given value for the standard electrode reduction potential for aluminium plus 3 ion is minus 1.66 volts and that of thallium plus 3 ion is plus 1.26 volt. Can you predict about the formation of M plus 3 ion in solution and compare the electropositive character of the two metals? Well, of course yes, but let me just help you. Standard electrode reduction potential values for two half cell reactions suggest that the aluminium has high tendency to make aluminium plus 3 aqueous ions, whereas thallium plus 3 is not only unstable in solution but is a powerful oxidizing agent also. Thus, aluminium plus 3 is more stable in solution than thallium plus 3. Aluminium being able to form plus 3 ions easily is more electropositive than thallium. Now, let us understand the reactivity of group 13 elements towards air. Boron is unreactive in crystalline form and aluminium forms a very thin oxide layer on the surface protecting the metal from further attack. On the other hand, amorphous boron and aluminium metal on heating in air form boron oxide and aluminium oxide respectively. With dinitrogen at high temperature, they form nitrides. When metal in its elemental solid state reacts with oxygen gas, it gives metal oxide. When metal in its elemental solid state reacts with nitrogen gas, it produces metal nitride. Boron trioxide is acidic in nature, which reacts with basic or metallic oxides to form metal borates. Aluminium and gallium oxides are amphoteric, while indium and thallium oxides are basic in their properties. Now, let us understand the important trends and anomalous properties of boron. The trichlorides, bromides and iodides of all group 13 elements being covalent in nature are hydrolyzed in water. Species like tetrahedral tetrahydroxy metal and octahedral hexahydroxy metal, except in boron, exist in aqueous medium. The monomeric trihalides being electron deficient are strong Lewis acids. Boron trifluoride easily reacts with Lewis bases such as ammonia to complete octet around boron. Due to the absence of d orbitals, that the maximum covalence of boron is 4, while since d orbitals are available to aluminium and other elements, their covalency can be expected beyond 4. Let us recall all the discussed concepts. The first one is the outer electronic configuration of group 13 elements is ns2np1. Second point is, as we move down the group, generally atomic radii increases but deviation is observed from gallium and aluminium. The third point is, similarly ionization enthalpy is expected to decrease down the group, but discontinuity is observed between aluminium and gallium and indium and thallium. The fourth point is, electronegativity first decreases from boron to aluminium and then increases marginally. The fifth point is boron is non-metallic with high melting point, whereas rest of the members are soft metals with low melting point. Sixth point is for group 13 elements, +1 oxidation state become more stable as we move down the group due to the inert pair effect. Seventh point is boron trioxide is acidic. Aluminium and gallium oxides are amphoteric and those of indium and thallium are basic in nature. Eighth point is boron does not react with acids and alkalis, but aluminium dissolves in mineral acids and aqueous alkalis as well. Ninth point is group 13 elements react with halogens to form trihalides except for thallium triiodide. Due to the absence of d orbitals, maximum covalence of boron is 4, but since d orbitals is available for aluminium and other elements, their covalency is expected beyond 4. Let me leave you with some interesting questions. Question number 1 is, why do white fumes appear around the bottle of anhydrous aluminium chloride? My second question is, why boron is unstable to form hexafluoroborate? Question number 3 is, why a discrepancy is observed in the trend of ionization enthalpy for group 13 elements? Dear learners, I hope that you have understood the concepts discussed. We will continue our discussion in the next episode. Till then, thank you.